All right, as promised, here's the day 2 video, the exciting conclusion for partial fraction decomposition. And you might be asking, well, what could be so much more complicated than that? A system with 4 equations? Well, let's find out. The first thing that could happen is you can have repeated linear factors. So that's like when one of the factors in the denominator appears more than once. You might have like an x plus 5 times another x plus 5, or an x plus 5 squared. We need to do a little bit something different when we set this up. And then, if we're being honest, it's going to be mostly the same as what we've seen before. So example 1 is this. And if we start our process like normal, we're going to factor the denominator. And we notice that we have an x minus 1 twice. So we could write it out as x times x minus 1 squared, and this is going to help us remember what we need to do. This is the new part right here. The setup needs to include not only an x minus 1, but an x minus 1 squared. And you could think about it, if we had an underneath the b and underneath the c, if both of them had a denominator of x minus 1, we could just combine like terms, or like fractions. So the way that we get a denominator of x times x minus 1 squared is we have to have a factor of x minus 1 squared. And this is just the way we're going to set it up. After that, everything else is going to be the same. It might look a little bit different in the work, but the process is the same. So our next step would be to multiply through by a common denominator. That common denominator is going to be x times x minus 1 squared. On the left side, like we've seen before, going to completely cancel out the denominator. On the right side, it's going to cancel out select factors of each of those fractional terms. So we get something that looks like this. And as always, on the right side, I kind of like to expand my x minus 1 squared, and I would like to distribute the x times x minus 1. And then once we distribute the a and the b and the c, we're going to group together our like terms. So my quadratic terms underlined in blue, my linear terms underlined in pink, and I can group them. I can factor out an x squared or an x, just like we have in the other problems. Then we can create a system. This one's going to have 3 equations. Blue, a plus b needs to be 3. Pink, negative 2a minus b plus c needs to be a negative 1. And hey, here's some good news. The constant, 5, is only going to be equal to a. So our system of 3 variables really, really quickly turns into a system of just 2 variables and 2 equations. We can substitute into equation number 1, a plus b equals 3. We'll plug in that 5. Turns out b is going to be a negative 2. And then if we plug in both the 5 and the negative 2 into our second equation, we get the value of 7 for c. And like we have in the other problems, we can replace the a, b, and c with those values. And there's our partial fraction decomposition when we have repeated linear factors. Okay, another thing that could go wrong. Not necessarily go wrong, but it could throw a wrench into things, is if we have an improper fraction. That happens when the degree in the numerator, or when the degree in the numerator is either equal to or larger than the degree in the denominator. So here we have x to the 4th on top, x cubed on bottom. It's improper because the degree on top is larger. So what we'll do is we'll just divide them. If we divide numerator divided by denominator, we go through the process of polynomial long division. We need to multiply by x. Distributing x through, we get x to the 4th plus 2x cubed plus x squared. Don't forget we're subtracting that green polynomial from the like terms above. And we we kind of get lucky here. We don't always get the first two columns or first two terms to go to 0, but they did. And what I have highlighted in purple there, now that's our remainder. And we know it's our remainder because its degree, 2, is smaller than what we're dividing by. We're dividing by a cubic. So what does this look like when we divide? Well, we have our quotient, and then we're going to make a separate fraction made up of the remainder divided by the divisor. Okay, and this fraction that I have circled, that's what we're going to decompose. That turns into its own separate decomposition problem, but we have to remember not to forget about the quotient that we got in our final answer. There's just going to be an extra term that has it. That is x, not that it has an x in it. It's just x. Okay, so we'll take that decomposition fraction that I have circled, set up the template, and then go through the motions just like we did in the last few problems. Now this one, if we do factor x cubed plus 2x squared plus x, we get a repeated linear factor. So just like in the last example, I have an a and a b and a c, and the c has an x plus 1 squared on the bottom. But otherwise, from this point out, it's going to be the same old, so I'll move a little bit quicker. Multiply through by the common denominator. When we do that, a bunch of stuff cancels. I'm going to expand or distribute where appropriate. And then kind of distribute the a and the b through. At this point, I would probably try to group the quadratic, linear, and constant terms. Here I have highlighted the equations that I'm going to write in my system, and there it is. Once again, third equation, a is already 6, so we can substitute that back in a few different places and find out what our coefficients are. A is 6, b is -1, c is 9. That means in my answer I have my quotient term x in green, and then 6 over x, -1 over x plus 1, and 9 over x plus 1 squared. And there's my decomposition. Okay, one more thing that could happen. This can actually be extended beyond just linear factors. We can also have quadratic factors. Take a look at example 3 and just look at the denominator. It's already factored for us. It would be kind of difficult to factor that one anyway. But we have x plus 1 times x squared minus 2x plus 3. And the important thing is x squared minus 2x plus 3 cannot be factored any further. Okay? When that happens, we can still do our decomposition, but it's going to need to look like this. And because the denominator of that second fraction is quadratic, we need the numerator to potentially be linear. Now, it's absolutely possible that the value of b could be 0, and then we just have constant numerators. But we have to be open to the possibility that we have a linear numerator there. That's the new part. Beyond that, and again, the work might look different, but the process is the same. We're going to multiply through by the common denominator. Stuff is going to cancel. This time, pay attention to the rightmost term. We'll have to FOIL that, and we're foiling it involving the b and the c. So we got x's, b's, and c's. Just be careful with your terms. When we expand, we get something like this. And like always, if we group our quadratic, linear, and constant terms, we get something that looks like this, which will allow us to write our system. And you see how all this is becoming, the same old. I can solve this one. This is probably the most complicated system we've solved from these examples. But I can combine equations 2 and 3 to make an equation 4. And then add equation 4 to 5 times equation 1 to eliminate a. Tells me that b is -1. And then pretty easily we can substitute some values back in, find out that a is 2 and c is 1. And no other tricks other than when you replace a, b, and c, b and c are both going to be in the numerator of the second fraction. So that's why I have a negative x plus 1 as that numerator. Okay, if we really wanted to press this, or if you absolutely had to do a problem like this where you had a cubic that was not factorable in the denominator, you would have something like a bx squared plus cx plus d in the numerator. But those tend to be a little bit more complicated, and of course you can extend the same procedure. You're just taking something that you already know and making it one step beyond. So we probably won't see too many of those. All right, we have a few more examples to practice in the day 2 practice set. Go ahead and complete those, check your answers, and that'll be it for our discussion on partial fraction decomposition.